Welcome to today's paper reading. Today's paper is titled, Rephrasing the Web, a Recipe for Compute and Data-Efficient Language Modeling. This paper was published on the AR14 preprint by Pratyush, Maini and colleagues from Carnegie Mellon University and Apple. Large language models are trained on vast amounts of web data, which is often unstructured, noisy, and poorly phrased. Current scaling laws indicate that training these models requires significant compute and data resources, which increases with model size. This is impractical due to high compute costs and the impending scarcity of high-quality data. In this work, the authors propose Web Rephrase Augmented Pre-training, RAP, which uses an off-the-shelf instruction-tuned model to paraphrase web documents in specific styles, such as like Wikipedia or in question-answer format, to jointly pre-train large language models on real and synthetic rephrases. The authors demonstrate that using RAP on the C4 dataset, which is naturally noisy, accelerates pre-training by approximately 3 times. At the same pre-training compute budget, RAP improves perplexity by more than 10% on average across different subsets of the pile, and enhances zero-shot question-answer accuracy across 13 tasks by more than 2%. The authors also investigate the impact of rephrasing style on model performance, providing insights into how the composition of training data can affect the performance of large language models in out-of-distribution settings. The gains are attributed to the higher utility of rephrased synthetic data, which incorporates style diversity that closely reflects downstream evaluation styles and has higher quality than web-scraped data. The introduction of this paper highlights the challenges in data curation for large language models, LLMs. One major issue is the ambiguity in deciding what data to pre-train on, given the limited availability of high-quality data and the need for computational efficiency. Synthetic data has been increasingly used in fine-tuning LLMs, but its generation process is often opaque and expensive, potentially leading to knowledge biases. To address these challenges, the authors propose the Web Rephrase Augmented Pre-training (RAP) method. This involves using an off-the-shelf LLM to rephrase web documents, which allows for more efficient learning and significant performance gains on out-of-distribution datasets. Figure 1 illustrates the RAP recipe for compute and data-efficient language modeling. Part A shows the process of using an off-the-shelf instruction-tuned model to rephrase articles from the web, which are then used in conjunction with real data to pre-train a large language model, LLM. Part B presents the zero-shot performance of GPT-1.3b models trained on various combinations of the C4 dataset and synthetic data variations, with each step representing a batch of 1 million samples. Part C displays the weighted average perplexity across 21 subdomains of the piled dataset for different model sizes and amounts of pre-training data. This figure highlights the effectiveness of the RAP method in improving model performance and efficiency. In the realm of neural scaling laws, Hoffman et al., 2022, introduced the chinchilla scaling laws, which show a linear relationship between model size and training data. This suggests that models like Gopher, Ray et al., 2021, were undertrained. For dataset selection, heuristics like Reddit Karma and document filters are used, while methods like Durimi, Xia et al., 2023, and deduplication, Abbas et al., 2023, improve efficiency. Data augmentation studies show both benefits, such as improved performance on reasoning tasks, Ganasekar et al., 2023, and risks, like mode collapse after multiple synthetic data cycles, El Muhammad et al., 2023. In this section, we discuss the rephrasing styles used in our approach. We categorize rephrasing into 4 styles: easy, medium, hard, and Q&A. The easy style aims for text that even a toddler can understand, while the medium style targets high-quality English similar to Wikipedia. The hard style uses terse and abstruse language, and the Q&A style is in a conversational question-answering format. To generate synthetic data, we utilize an instruction-tuned Mistral 7B model, which is prompted to rephrase text from web-crawled datasets. Each rephrased example is limited to a maximum of 300 tokens to prevent information loss. Our method also combines real and synthetic data in a 1-to-1 ratio, ensuring that the language models are exposed to both high-quality synthetic data and the noisy web text, thereby enhancing their robustness. Figure 2 illustrates the comparison of perplexity on the piled dataset for a 1.3B language model trained for 300 billion tokens. The figure clearly shows that the RAP method, which combines C4 data with QA85B synthetic data, significantly outperforms models trained solely on twice the amount of real C4 data. This result highlights the effectiveness of RAP in reducing perplexity, indicating better generalization capabilities on out-of-distribution datasets. In this section, we discuss the perplexity evaluation of the pre-trained model on out-of-distribution datasets. The evaluation is conducted on 21 subdomains of the piled dataset, each consisting of the first 10,000 documents from their respective domains. Additional details about the evaluation process can be found in Appendix D. The models evaluated were either trained on the C4 dataset or a stylistic rephrase of it. It's important to note that the perplexity is evaluated on the piled dataset rather than C4. This choice results in a small increase in perplexity on the C4 validation set, less than 1 perplexity. This increase is due to the models being trained on multiple text distributions, both synthetic and real web, which does not minimize the risk over the C4-only distribution. To compare the models meaningfully, we evaluate the generalization capability on 21 different domains of the pile. The results for each domain are presented in Figure 2. In this section, we evaluate our pre-trained language models on various zero-shot question-answering benchmarks. We assess our models on a total of 13 different zero-shot benchmarks, which include categories like general understanding and specialized knowledge. The general understanding category tests broader cognitive skills and language comprehension, while the specialized knowledge category demands expertise in specific domains. We compare the performance of models trained on mixtures of real and synthetic data with those trained on various splits of real data. Notably, models trained on synthetic data combined with the C4 dataset exhibit higher average performance, indicating that synthetic data can enhance general understanding capabilities. However, we also observe that synthetic data cannot impart new knowledge but can help pre-train faster. This section highlights the importance of real data and the potential benefits and limitations of using synthetic data in language model pre-training. Table 1 evaluates tilde-operator 1.3b parameter language models on general understanding tasks across datasets, focusing on reasoning, language comprehension, and common sense. The results indicate that models trained on a combination of synthetic data and the C4 dataset, synthetic plus C4, show an overall higher average performance of 49.4% compared to those trained solely on the real C4 dataset, which scored an average of 47.4%. This suggests that synthetic data can enhance general understanding capabilities. Additionally, the Tiny Llama model, despite being trained on 10x more data, performs comparably to models trained on real data, indicating minimal gains from adding more real data. This highlights the potential of synthetic data in improving model performance. Table 2 evaluates large language models with approximately 1.3 billion parameters on tasks requiring specialized knowledge in domains like science, medicine, mathematics, and logic. The results for RAP are averaged over 3 runs. Key findings include that synthetic data does not provide new knowledge, larger datasets enhance performance, and the Pythia model trained on 300 billion tokens outperforms the C4 dataset with 85 billion tokens. Table 3 evaluates the impact of real data on the performance of tilde-operator 1.3b parameter language models trained for 150b tokens on general understanding tasks. The results indicate that incorporating real data significantly enhances model performance when pre-training on Medium or Wikipedia-style paraphrases. Notably, while synthetic data alone shows strong performance, adding real data to the synthetic model reduces performance on the truthful QA dataset by 4%, suggesting a potential dilution effect. This table highlights the nuanced benefits and trade-offs of combining real and synthetic data in language model training. Figure 3 illustrates the significance of real data in pre-training language models by comparing perplexity on the piled dataset. The models, which have 1.3 billion parameters, were trained for a total of 150 billion tokens using a subset of the C4 dataset containing 35 billion tokens. The figure highlights the performance differences when pre-training on C4 data combined with synthetic data versus using synthetic data alone. This comparison underscores the importance of real data in enhancing model performance. In this section, we delve into the analysis of data combination and method ablations to understand how to enhance performance optimally. Firstly, regarding data combination, we investigate the importance of real C4 data. Our findings indicate that while synthetic data using QA prompts is sufficient for strong performance on QA tasks, there is significant degradation in perplexity across various subdomains when evaluated on pile perplexity. This suggests that synthetic data, being very clean and structured, lacks certain special characters and styles present in real data. Secondly, we explore whether combining multiple synthetic datasets improves performance. We measure the impact of combining multiple synthetic styles with C4 for training in 1:1 and 1:2 ratios. Our results show that for zero-shot QA tasks, combining multiple styles does not yield performance benefits compared to using only QA and C4 data. Lastly, in method ablations, we examine the importance of a high-quality rephraser. We find that pre-training on data generated by smaller rephrase models like Qwen 1.8b and Mistral 7b achieves lower perplexity than Vicuna 13b. Additionally, we test whether synthetic data improves over augmentations and how the style of synthetic data impacts performance on specialized domains. Our findings suggest that synthetic data enhances the learning process and that training with diverse data styles is crucial for LLM generalization. Table 4 evaluates the impact of real data on the performance of tilde-operator 1.3b parameter LLMs in specialized knowledge tasks. The results indicate that incorporating real data enhances model performance, particularly when pre-training on Q/A style paraphrases. This table highlights the importance of real data in improving the accuracy and effectiveness of language models in specialized domains. Table 5 evaluates the performance of tilde-operator 1.3b parameter LLMs trained for 150b tokens on specialized knowledge tasks. The results indicate that combining rephrasing styles does not improve performance on zero-shot tasks compared to using just Q and a style. This suggests that the diversity of styles does not necessarily enhance the model's ability to perform in zero-shot scenarios, highlighting the importance of specific training strategies for different task requirements. Table 6 presents the evaluation of approximately 1.3 billion parameter language models trained for 150 billion tokens on general understanding tasks. The results indicate that combining multiple rephrasing styles does not provide a performance advantage on zero-shot tasks when compared to using just the Q and a style. This suggests that for these tasks, the simplicity of the Q and a style is more effective than the complexity introduced by combining various rephrasing techniques. Figure 4 illustrates the impact of combining multiple styles of synthetic data on perplexity across various domains of the pile. The models analyzed are 1.3 billion parameters and were trained for a total of 150 billion tokens. The results indicate small improvements in perplexity when multiple styles of synthetic data are combined. Figure 5 illustrates the importance of using a high-quality paraphraser in the RAP framework by comparing the perplexity across various domains of the pile dataset. The results demonstrate that models like Qwen 1.8b, despite being smaller, can produce paraphrases of high quality, which helps in maintaining lower perplexity. Conversely, the fine-tuned T5 base model, which is of lower quality, leads to significantly higher perplexity in language modeling tasks. Despite this variation in performance, all the paraphrasing models contribute to reducing perplexity when compared to using only real C4 data. This highlights the value of synthetic data in enhancing language model performance. Figure 6 illustrates the comparison of perplexity on the piled dataset for various augmentation strategies. The models, which are 350M parameters in size, were trained for a total of 15B tokens. The results show that RAP, medium plus C4, significantly outperforms traditional augmentation methods in terms of perplexity. Figure 7 illustrates the impact of various styles of synthetic rephrases on perplexity across all domains of the pile. The study involves training 128M parameter models for 3 billion tokens to evaluate the performance differences when using different synthetic data styles. The styles include easy, medium, hard, and Q&A, each of which is tested to understand its effect on model perplexity. The results indicate that while no single synthetic style dominates across all domains, a diverse combination of styles can significantly improve perplexity, highlighting the importance of style diversity in synthetic data for effective language model training. Figure 8 presents a comparison between synthetic and real data from the C4 corpus, demonstrating that synthetic data effectively preserves the semantic meaning of the original C4 data while primarily altering the stylistic elements. This is shown for both medium rephrases of C4 in Part A and QA rephrases of C4 in Part B. The analysis reveals high cosine similarity between real and synthetic data pairs, indicating that the synthetic rephrases maintain similar meaning to their real counterparts without introducing extraneous information. This suggests that the performance gains observed are not due to knowledge leakage from the rephrase models but rather the successful maintenance of semantic integrity and stylistic variation. The applications of RAP span both low-resourced and data-rich settings. In low-resource scenarios, synthetic data is a natural solution, outperforming in-domain data alone. However, in data-rich settings, the viability of synthetic data remains a question. The cost of generating synthetic data versus training on extra real data is a key consideration. For instance, generating 85B tokens can account for 25K GPU hours, while training on 300B tokens can take 6K GPU hours. Recent advancements in model efficiency suggest potential cost reductions. Additionally, synthetic data generation offers advantages such as being a one-time investment and highly parallelizable. However, ensuring diversity in synthetic data remains a limitation. Diversity in both style and knowledge is crucial, and recent studies highlight challenges in maintaining content diversity. This remains an area for future research. In this paper, the authors explore the use of synthetic data in pre-training large language models, LLMs. Synthetic data offers several advantages, including the ability to embed desirable attributes such as fairness, bias mitigation, and specific stylistic elements directly into the data, thereby reducing the need for specialized adjustments in the training algorithm. This approach provides an alternative method for aligning language models with human values. The authors also highlight the growing interest in synthetic data for instruction tuning and pre-training, emphasizing the importance of understanding the properties of the data used. They discuss two significant benefits of synthetic data: its value in scenarios with limited high-quality data and its potential to enhance generalization across different text domains and styles underrepresented in the training dataset. However, the paper also acknowledges the challenges and limitations of synthetic data, such as the high cost of generation, the difficulty in ensuring diversity, and the limitation in learning new knowledge. The authors suggest that practitioners must make critical decisions regarding the quality of the synthetic data generator, the balance between real and synthetic data, and the point at which training on synthetic data reaches diminishing returns. This work represents an initial step towards addressing these questions and demonstrates the potential of synthetic data to improve the efficiency of LLM training in terms of both compute and data size. Thank you for watching.